Hello everyone, this is Calculus Lecture 4, and today we'll quickly review the rules of derivatives we learned last time, and then our main focus will be to use what we learned to solve some problems. So let's get started. I first just want to quickly review the rules for derivatives. So let's start with a constant function. So if we have f of x equal to c, where c is some constant, then the derivative is going to be 0. Now, if we have any power in general, we get the power rule. So f of x to the n, where n is any number, f of x equals x to the n, right? And n can be any number, it does not have to be an integer. And then we have f prime of x equals n times x to the n minus 1. In particular, for example, if we have the square root of x, then we would get 1/2 x to the negative 1/2. And if we had 1 over x, well, that's x to the negative 1, so we would get negative x to the negative 2. So those are good ones to keep in mind. We also have e to the x, the exponential. So if f of x equals e to the x, then f prime of x is also equal to e to the x. If f of x is the natural log of x, there are formulas for the general log as well, but we'll just quickly review the natural log. So if f of x is ln x, then f prime of x is 1 over x. And finally, we have our trig functions. I'll skip the inverse trig functions, but just go over the three main ones. So if we have f of x equal to sine x, then f prime of x is cosine x. If f of x is cosine x, then f prime of x is negative sine x. And if f of x is tangent x, then f prime of x is secant squared x. And remember, secant is 1 over the cosine. So this is just 1 over cosine squared x. And finally, we'll have some rules that we can follow. So if we multiply by a constant, then the derivative just gets multiplied by a constant. So the derivative ddx of c times f of x, where c is some constant, that's equal to c times f prime of x. We have rules for sums and differences, so now we're going to assume that f and g are two functions of x. Then f plus g, so the sum, f plus g prime of x, we just add the derivatives, so that's f prime of x plus g prime of x. We can do the same thing for subtraction, so f minus g prime of x is f prime of x minus g prime of x. And finally, we have the product, quotient, and chain rules. So the product rule, we have f times g prime of x is equal to f prime of x g of x plus g prime of x f of x. We also have the quotient, f over g prime of x, assuming that g of x is non-zero, is going to be equal to g of x f prime of x minus g prime of x f of x over g of x squared, or g squared of x. So again, the mnemonic to remember this is low d high minus high d low over low low, where low is, or where d represents the derivative. So finally, we have the chain rule, which again, we will go over in the later lecture, but just so that you know it. So this one here was the quotient, and then we'll do the chain rule. So this is where we're looking at a composition of functions. So we're looking at f of g of x and f of g prime of x. We're going to do f prime evaluated at g of x times g prime of x. And we'll do a lot of practice with that later, but it's good to get used to the formula. Now let's do some practice problems. One more piece of notation that I haven't introduced yet is this. So say I have f of x given by some formula, and I ask you for, or y equal to f of x, say, and I ask you for dy dx, and then I put a vertical line and a number below. So that's asking you to do is find the derivative and then evaluate at 3. That's what this line means. So let's do some practice. Here's the first problem. Say y equals x squared minus 4x plus 3. The question is to compute the derivative evaluated at 3. I'll pause for a minute and then explain the answer. All right, so to find the derivative, before evaluating, we always first just compute the general derivative. So we're going to have dy dx equals, and then we're just going to use the power rule. So the derivative of x squared, we just pull the 2 down and decrease the power by 1, so that's 2x. All right, minus 4 from this term. And the 3 is constant, so the derivative is 0, and we don't have to write down anything there. So here's the derivative, 2x minus 4, and then we have to evaluate that at 3. So then we have dy dx evaluated at 3. That's equal to 2 times 3 minus 4, and that's just 2. So the final answer would be 2. All right, and then this question has a part 2. And now the question is, we want to compute the equation of the line tangent to the graph of y equals x squared minus 4x plus 3 when x equals 3. So basically at this point 3, we want to find the equation of the tangent line. Okay, so we actually know the slope of this line is 2 because we just found the derivative. Now I'll just pause for a moment and see if you can try and figure out what the equation for the line should be. Remember that now that you know the slope, you just need 1 point on the line. All right, so, well, the point on the line is going to be the point at 3, because the tangent line, whenever we have some graph and we have some point on it, the tangent line will always pass through that point. So if we're looking at 3, then the point where x equals 3 on this graph will be on this line. So all we have to do is plug that in. So when x equals 3, we're going to have y equals 3 squared minus 4 times 3 plus 3. All right, so that's 9 minus 12 plus 3, which is 0. So the point on the line that we know is going to be 3, 0. And then we know the point on the line, and we know the slope. So we can just write down the equation y equals 2 times x minus 3. I believe that's right. So that's going to be the equation of the line tangent to the graph. So this is like some quadratic. Sorry, it's some quadratic like this. And at the point x equals 3, we found the equation of this line tangent. All right, here's another example that's going to be a little bit trickier. So the question is, find the equation of the line tangent to y equals sine of x when x is equal to pi over 6. All right, and again, I'll just pause for a moment here. Feel free to pause the video and take as long as you need. And just a hint, the derivative of sine of x is cosine of x, so you'll need to use that. Okay, so again, the strategy is to find the slope of the line and then a point on the line. So the slope is the derivative, and the point on the line is just going to be you plug in this point into the function. So let's first find the slope. So the slope of this line, okay, at this point at pi over 6, that's going to be dy dx evaluated at pi over 6. So what is dy dx? Well, y is equal to sine of x. So dy dx is the derivative of sine of x, which is cosine of x. And since we're evaluating that at pi over 6, this is going to be cosine pi over 6, which is root 3 over 2. And then the point on the line, we're just going to substitute. So x is going to be pi over 6. And then y is going to be sine of pi over 6, which is 1/2. And then we can write down the formula for the line. So we're looking for a line that goes through this point, pi over 6, 1/2, and has slope root 3 over 2. So that's going to be y minus 1/2 equals root 3 over 2 times x minus pi over 6. And you can simplify that to whatever form you need. This is going to be the equation for the line. All right, let's do one example working with a graph. So I'm going to draw a graph and write down the question here. So we're going to have a line segment going from 0, 3 to 1, 3. Then it's going to go down to 0.31. And you can assume all pieces of the graph are linear. And then it's going to go horizontally until 6, 1. So the points on the graph here are 0, 3, 1, 3, 3, 1, and 6, 1. And the questions are, first, find the derivative at x equals 5. So find dy dx evaluated at 5. All right, then find the slope of the tangent line when x equals 2. And finally, find dy dx when x equals 3. So I'll give you a moment. Part C is going to be especially tricky, and it's something we haven't actually discussed before. But see if you can guess what the answer is. All right, so first we're going to be evaluating at 5. So we're going to look at x equals 5. This is the point on the graph. And the tangent line at that point is just going to be horizontal, because the entire graph is horizontal. And the slope of any horizontal line is 0. So we know that the derivative evaluated at 5 is 0. All right, now when x equals 2, now we're on this point. And because the graph is linear around this point, we're just going to be able to draw the same line. So this is going to be the tangent line. And we can just find the slope because we actually know 2 points on it. So we know that 3, 1, and 1, 3 are points on it. So all we have to do is use rise over run as the slope formula. So 1 minus 3 over 3 minus 1 equals -1. And that's going to be the slope. And note that the slope of the tangent line just means the derivative. They're just different words for the same thing. And finally, the last question is to find dy dx when x equals 3. Now, this is a little challenging because how are we going to draw this graph? Like, we could do that, or we could do this, or anything in the middle, conceivably. So in fact, when a graph is pointy like this is an example of a graph that's continuous, but where the derivative does not exist at this point. So when we have spikes in a graph, even if the graph is continuous, the derivative may not exist. When the derivative does exist, we call it differentiable. And it does not always have to exist. In fact, there's an example of a function called the Weierstrass function, which is super interesting. Let me just write down that name in case you want to look it up. Because it's continuous everywhere, but not differentiable at any point. So it's like spiky at every single point, which is very interesting. All right, now let's talk about higher order derivatives. So we talked about notation for this once before, but let me just go over it again real quick. All right, so firstly, higher order derivative just means you're taking the derivative multiple times. That's all it means. So what we do is if we have one derivative, we have f prime of x. For 2, we would have f double prime of x. For 3, we'd do f triple prime of x. So 3 derivatives. For more than 3, we don't really like drawing that many apostrophes, so instead we're going to do f and then some number in parentheses. So f57x. That means you're taking the derivative 57 times. Remember that you do need the parentheses here. If you don't have them, that would mean you're taking it to that power rather than taking a derivative that many times. So you always need to have those parentheses there. Now, the other way you could notate this is using the dy dx or just ddx notation. So to do a double derivative, that's d squared y over dx squared. Note where the number goes, it goes between the d and the y, but after the x. So, or just d squared over dx squared. Then for a cube, you could do d cubed y over dx cubed. All right, so this means the same thing as f triple prime. Same here. And you could do that with any number you want. So just some questions for practice. What's the third derivative of x to the fourth? What's the third derivative of 5x cubed? And finally, what's the first derivative of 6x? We'll just pause for a moment. All right, so to find the third derivative of x to the fourth, we just take the derivative 3 times. So the first time we pull down the 4 and reduce the power by 1, so we get 4x cubed. Then we do it a second time, so now we pull the 3 down and multiply it by the 4. So we're going to get 12 and then x squared, because we're again decreasing the power by 1. And then we're just going to do that one more time. So we pull the 2 down, multiplied by the 12. That's going to be 24x. Just x to the 1 or x. The second one's similar, so we start with 5x cubed. Differentiate ones, 3 gets pulled down. 3 times 5 is 15. So that's 15x squared. Okay, do that again. The 2 gets pulled down. 2 times 15 is 30x. And one more time, that's just 30x. So you can think of that as 30x to the 1. The 1 gets pulled down and becomes a 0. So that's just going to be 30. X to the 0, which is just 1. And finally, what's the first derivative of 6x? So now we're just back to what we were doing before, taking the derivative 1 time. And this is just a constant times x, so the answer is just going to be 6. Now, I could also ask you to evaluate one of these at a point. So if you were to get something like 24x, and then I said evaluate this at the number 2, then you would just multiply 24 times 2, and you would get 48. So let's practice that a little bit. So say y equals 2x to the 4th. The question is to find d squared y over dx squared, so that's the second derivative, evaluated at 3. So again, I'll just pause for a moment. Feel free to try that out. Okay, so now the d squared y over dx squared means we're taking the derivative 2 times. So we're going to differentiate once, and that's going to give us, well, we pull the 4 down and get 4 times 2, which is 8, and then decrease the power by 1, so we get x cubed. And then we do that one more time. So we pull the 3 down. 3 times 8 is 24, x squared. So this is the derivative, and now we're going to evaluate at 3. So that's going to be 24 times 3 squared, so 24 times 9. And that'll be the answer. Let's do one more for practice. Say f of x equals 3x squared. The question is to find the third derivative, d cubed y over dx cubed, evaluated at 2. And once again, I'll just pause for a moment and then explain the answer. All right, so let's do this. So we're going to be taking this derivative 3 times. This is going to be interesting because 3 is actually bigger than this exponent, so we might get something slightly surprising. So the first time we differentiate, we pull the 2 down. 2 times 3 is 6x, right? Because we just decreased that power by 1. Then we do it again. So the 6x, we differentiate, we just get 6. As the 6x to the 1, the power got decreased. So now we just have a constant. And then when we differentiate that constant, we just get 0. And 0 evaluated at 2 is still 0. So the final answer is just going to be 0. And that's in general true if you have a polynomial and you differentiate more times than its degree. You're always going to get 0 because you always decrease the degree by 1 every time you differentiate. All right, so here's a little exercise to get you used to the notation, because for all of this, we've been using dy dx, but y and x aren't going to be the only variables you see. So for example, in physics, you might see dx dt, where like x is position and t is time. So just to get you used to this, I'm going to write down some equations, and I just want you to think about what the notation for the derivative would be. You don't need to actually find the derivative. So here are 6 exercises. So first t equals 2x, h equals 12w, v equals d squared plus 3d, right? W equals 5f squared, j equals 10k plus 6, and finally f equals 9g minus 2. So feel free to pause and try and write down just the notation for the derivative. You don't actually need to solve it. All right, so the first one, we're looking at the derivative of t with respect to x. So we're going to look at dt dx. All right, then for this one, we're going to have dh dw. All right, for this, we have v as a function of d. So we're going to do dv dt. I don't like that notation very much, but yeah, normally it would be better not to use d over here, but anyway. All right, over here we would have dw df. Over here we would have dj dk. And finally here we would have df dg. All right, now I'd like you to take a minute and try and work out what these would be in terms of whatever the variables are. And again, I'll give the answers in just a moment. All right, so these are all going to be with the power rule. So over here we have 2x. That's just a scalar multiple of x, so we're just going to be left with the constant 2. Same here with 12w, we're just going to be left with 12. Here we use the power rule. D squared, the derivative is 2d. We pull the 2 down. Plus 3. 3d is just a constant multiple of d, so we just get 3. dw df will be, so we're pulling the 2 down, multiplying by the 5, so 10f. Okay, this one's just going to be 10 from the 10k. The constant doesn't matter because we just get 0 when we differentiate a constant. And finally, the same thing here, we're just going to get 9 from the 9g term, and the minus 2 doesn't matter. Let's do some more examples. So here's a practice problem. Let y equal 3u to the 5th. All right, and find d squared y over du squared. So note that we're using u as a variable instead of x right now. Evaluated at 2. All right, and so what we're going to do here is we're just going to differentiate this twice. So the first time we pull the 5 down, 5 times 3 is 15, and then decrease the exponent to 4. So that's 15 u to the 4. And then we differentiate one more time. So we pull the 4 down. 4 times 15 is 60 u cubed. And then we're going to evaluate that at 2. So the final answer is going to be 60 times 2 cubed. So 60 times 8. Which I believe is 480. All right, example 2 is going to be similar again. So we're going to let x equal 2t to the 6th. And we need to find the third derivative, d cubed x over dt squared. Sorry, dt cubed, evaluated at 1. So feel free to give that a try. All right, so we have x equals 2t to the 6th, and we're going to take the derivative 3 times. So the first time we get 12t to the 5th. All right, then the second time, pull the 5 down, that's 6t to the 4th. And then the final time, we pull the 4 down, so that's 240t cubed. And then we evaluate at 1, so 240 times 1 cubed, which is just 240. All right, 3 more examples to go. All right, this one's going to be a little bit trickier, but see if you can figure it out. So number 3, let f of x equal 1 over x squared. Find the triple derivative, f triple prime, of 2. And just keep in mind, if you're having a hard time solving this, think about a different form you might prefer to write x squared in. You don't really want to use the quotient rule for something like this. All right, so the form we want this in is we want to write f of x as x to the minus 2. And this is because now that we have it as a power of x, we can use the power rule, which is much nicer than any other rule. So now we just differentiate this. We want to differentiate this 3 times. So we're going to go x to the minus 2, and then the first time we differentiate, we bring the -2 down. So it's -2x to the -3. Then we differentiate a second time. Just to keep track, I'll write down how many times we've done this. Then we pull the -3 down. -3 times -2 is a +6. X to the -4. And then we differentiate a third time and final time. We pull the -4 down. We get -24 x to the -5. And that's going to be the third derivative of f. And then we evaluate this at 2. So we're going to get -24 times 2 to the -5th. Or -24 over 32. And you can simplify that if you want. I think that's going to be -3/4. All right. Let's say f of u is 3 over u cubed. Find f double prime of u. And you want to try and use the same trick as last time. So again, I'll just give you a minute. All right, so again, we're going to do the exact same trick. We're going to write f of u as 3 times u to the -3. And what that allows us to do is use the power rule. So now we're going to take the derivative one time, and we're going to pull the -3 down. We'll get -9 u to the -4 when we decrease the power by 1. And then we do that a second time. So we pull the -4 down, that's 36 u to the -5. And this question didn't tell us to evaluate, so that is just our final answer. All right, let's do one more and then we'll do a bonus problem. All right, so let g of t equal t squared plus 2t plus 6. All right, find g double prime of 2. Okay, so we're going to take the first derivative just by using a power rule. So the derivative of t squared is 2t, right? And then the derivative of 2t is 2. And the 6 goes away when we differentiate, that's just 0. And then we differentiate one more time. So this 2 goes away, and all we're left with is the derivative of 2t, which is 2. And so the 2 is our final answer. All right, let's just quickly do a bonus problem. Find the derivative of x plus 1 to the 7th. So feel free to take a minute. All right, so one way you could do this is expand out x plus 1 to the 7th. You'll get a long polynomial, and you can differentiate each term using the power rule. But that would take a very long time. So instead, a way to do this is to take the chain rule. So this is the composition. If you have f of x equals x to the 7th, and g of x equal to x plus 1, this is the composition, f of g. And so you can use the chain rule. So you take the derivative of f, which is 7x to the 6, but then you plug in g. So instead of this x over here, you actually plug in x plus 1 times the derivative of g of x, but the derivative of g of x is just 1. So that doesn't actually do anything. So times 1, And so the final answer to this will just be 7x plus 1 to the 6th. So the chain rule is a much simpler way of solving something like this with a giant power than, say, actually multiplying using the binomial theorem and then differentiating term by term. So we'll see that the chain rule is very useful. All right, and then I think we'll end there for today. And then next time we'll continue talking about the derivatives.